Hey everybody, welcome back to your regularly scheduled programming. Today we are solving LeetCode 206, which is called reverse linked list. The question asks us, given the head of a singly linked list, reverse the list and return the reversed list. I have a linked list set up here with 3 nodes, so 1, 2, and 3, and the final node in the linked list is null. So just keep that in mind. On the LeetCode examples, they don't actually show that last node pointing to null, but in a linked list, the final node is actually null. I'm going to be showing you 2 approaches. The first one is going to be the iterative approach, and then we'll go over the recursive approach. In our iterative approach, we're going to be solving it by keeping track of 3 pointers. So the current pointer is going to represent the current node, so the current node we're exploring. The previous pointer is going to be keeping track of the previous node. And as you guessed it, the next pointer is going to be keeping track of the next node. Our reversal strategy is going to be by setting the current node's next pointer, so that's current.next, to the previous node. So each list node actually has an intrinsic attribute .next, which represents the next node after it. That's just provided by us as part of the list node definition. So what that looks like, this reversal is just current.next is going to be equal to previous. I'm going to demonstrate this process below. So if current node is equal to 1, where this red arrow is, then our previous pointer is equal to null. So like I mentioned earlier, the last node, you can think of the last node in a linked list pointing to null. I think it's common that you can also think that way of the previous pointer to the head. So you can just think of it, since it's empty or whatever, it's pointing to null as well. And then the next node is going to be just current.next, and 1.next is equal to 2. So we have our next pointer equal to 2. And I have just rewritten this up here. So setting current.next, so current is 1, its next pointer is going to be equal to prev, and prev is null because there's nothing there. And so that's what that will look like. So we went from 1 pointing to 2 to 1 pointing to null. And that's the current state of our linked list. Next, we're going to be updating the pointers on each iteration. So the previous pointer, so if we move this red pointer, right? Previous to this pointer is 1. So we would have had to update the previous pointer to when cur was equal to 1. So previously, this red arrow was on 1, and we'd have the context to appropriately update the pointers. And then the current pointer would be set to next, because next was actually equal to 2. And then now we're set up for the next iteration. So now we have the current node pointing to 2. The previous node in the sequence is 1, and the next pointer is current.next, which is equal to 3. We're going to reverse it by setting current.next equal to prev. So current is 2, its next pointer is equal to prev, which is 1. And we know what 1 looks like. It's 1 is pointing to null. So this is just right from here. So 1 to null. Awesome. We update our pointers. Previous is equal to current, which is equal to 2. And then current is equal to next, which is equal to 3. Now we're set up to go to the final node. Sorry for the messiness, but our current pointer is now 3. The previous node in the sequence is 2, and the next pointer is current.next, which is equal to null. We're going to be doing a reversal by setting cur.next. So cur is 3, its next pointer is pointing to prev, which is 2. And 2 looks like this, which is pointing to 1, which is pointing to null. And so we have 3, 2, 1, null. And that is the full reversal. We'll be updating our pointers, which is prev is equal to current, which is equal to 3, and current is equal to next, which is equal to null. And that's when the loop that we're performing these operations in will terminate, because we will no longer have a valid current node. When we're here, it's going to end. So as you can see, we have a successful reversal. We went from 1, 2, 3 pointing to null to the other way around, where it's 3, 2, 1 pointing to null. And the strategy works. Here is the code for our iterative approach. We'll initialize our 3 pointers first. So the current pointer is going to be pointing to the head, which is the first node in the linked list. Our previous pointer and our next pointers are going to be pointing to null initially. Inside of a while loop, we're going to be checking that we have a current valid node. So while it's not null, we're going to be carrying out our operations. So we'll find the reference for our next node, which is just current.next. We're going to be reversing it. So current.next is equal to previous, where we're just setting the next pointer for the current node equal to the previous node. And then finally, we're updating our pointers. So the previous node is going to become the current node, and the current node is going to become the next node, and this will set us up for the next iteration. Finally, we'll be returning the previous node, because by the end, the previous node is going to be pointing to the final node in the sequence, and when that's reversed, it's going to be this first one technically, and it's going to have the context for the rest of the entire linked list. If I run this, awesome, and then we can submit it. There you go. The time complexity for this iterative approach is O of n, where n represents the size of the linked list. We're going to have to be traversing through every single node in the linked list. We'll be going over them at once, and that's going to result in O of n time. Our space complexity is O of 1 because we're not actually storing anything that's representative of the size of the linked list. We're just holding on to these pointers, and those are constant in space. Alright, let's go over the recursive approach now. We're going to be going over the same example of this linked list, 1, 2, 3 pointing to null. But first I want to start off with a little sample just to get us up to speed with this approach. So there's going to be a smaller linked list of just 2 nodes, 1 pointing to 2, which then points to null. The reversed list is going to look like this, where 2 is pointing to 1, which is pointing to null. Essentially, all that happens here is just that this 1 and 2 are being swapped, right? That's the only difference in this. To break it down a step further, we can take a look at exactly what these nodes were pointing to and then what they end up pointing to. So note in the reversed list, 2 is pointing to 1. Initially, it's pointing to null. So we need to make sure, so that's the first thing we need to do. We need to make sure 2 is pointing to 1. Then 1 is pointing to null in the reversed list. Initially, what we're given is 1 is pointing to 2. So that's the second thing we have to change. So let's start off with the head. So if our head is equal to 1, we have access to the next pointer by just using head.next, and that's 2. Head.next is equal to 2. We can also do, this is also completely valid, head.next.next, and that'll give us access to the null. So right now we've encapsulated the entire linked list with these 3 variables, head.next, and head.next.next. Now, like I mentioned, we need to change 2 to point to 1 instead of null, and we can do that by just replacing 1. So 2 is pointing to null, we just need to change this null to 1. And we have access to null, it's just head.next.next. And we have access to 1, that's just the head. So if we just do head.next.next is equal to head, we'll have effectively replaced null with 1. That's just going to look like this. So 1 is pointing to 2, and then that's dot next, and then the dot next, head.next.next becomes 1. Really, it looks like this, where it's a circular linked list, but it's just easier for me to visualize it like this. So then to break the circular nature of this, what we need to do is establish the second part, which is 1 needs to point to null. Right now it's pointing to 2. And all you need to do for that is just do head.next is equal to null. And then this 2 to 1 is still valid from what we did previously, but now this 1 goes away from pointing to 2, and instead it points to null. And that would be the successful reversal of this little sample we have. It's the exact same what we're going to do for the bigger example. I just wanted to start off with a little smaller example. I've written out the code here to help us understand it a little bit better. I think that's going to be more effective in explaining the bigger example. So we have a function called reverse list. It takes in a head node. We have a base case. We check if the head is equal to null, or if the head.next pointer is pointing to null. And if either of those are true, then we'll return the head. Otherwise, we're going to be initializing a reversed list head variable that's going to be making a recursive function call to reverse list with head.next. That's going to run until we're at the last node, basically, because at that point, this head.next is equal to null. It's going to get activated, right? If the head is equal to 3, then head.next is null, and then at that point, we'll return head. Then we'll continue with the rest of the function. So head.next.next is equal to head.next is equal to null. That's just the reversal strategy we just implemented here. So I hope that's clear to you. And then finally, we'll just return the reversed list head. At that point, it's going to be equal to 3 for this example, and that's going to be our entire reversed list. Let's run through this example using this code. So RL is just representing reverse list. I've just done a short form version of it to make it a little bit easier to write. So we're passing in the initial head, which is 1. So RL at 1. I've squared off the actual function calls just so they're a bit more clear. First thing we're going to do is check the base case. If the head is equal to 1, it's not equal to null. Is head.next equal to null? Well, no, it's not. It's equal to 2. So our base cases are invalid. I've put an X right beside it. Now we can move on to the next part. Let reverse list head is equal to reverse list at head.next. So we know that our head is equal to 1 and our head.next is equal to 2. So RLH is just reverse list head and is going to be making a recursive function call to reverse list with head.next, which is equal to 2. So now we start out from the top again. Here's our new function call, our first recursive call, and we check if the base case is valid. 2 is the head, it's not null. Head.next, 3 is not null either, so we don't return the head, and we'll define RLH again as the reverse list function call with head.next. And if the head was 2, then head.next is 3, so that's why we pass in RL at 3. Now this is the final recursive call, and we'll check if the base case is valid. If head is equal to null, head is equal to 3, so it's not null. Is head.next equal to null? It is, so we'll return the head. So the base case is valid, we have a check mark, and we return the head, which is equal to 3. So RL at 3, the result of that is just return of 3. So we go back up the call stack now, because that's the deepest we went without returning. So we just ended up returning on that RL at 3, and now we store the result of that in RLH. So now we can move on to the next parts. So the first part is head.next.next is equal to head. So head is equal to 2. 2.next is 3. 2.next.next is back to 2. Initially that was null, but now we're setting it to 2. Exact same thing that we did out here. The second part of that is setting the next pointer, head.next, to null. Just so we can break the circular nature of the infinite linked list. And combining those, we end up getting 3 pointing to 2 and then 2 pointing to null. So you can see this starting to take shape. Finally, we return the reversed list head, and that's just equal to 3 here. And that's going to, now we work our way back up the call stack. So we're at the first function call now. We returned RLH is equal to 3, so RLH is going to be storing that. RL at 2 ended up returning RLH at 3, so that's why we have that there. And now we can continue with the rest. So we do a head.next.next, 1, 2, 1. That's exactly what we did here. So just think of that as over here. Head.next is equal to null, so 1 points to null. 1 is our head, right? And combining those, we get this. So 2 pointing to 1, and then 1 points to null. Finally, we return RLH equals 3. So the original function call of reverse list with the head of 1 will return node 3. And by this point, node 3 is fully defined as the reversed list. And we can just walk through that real quick. So 3 points to 2, and that 2 was originally pointing to null, but from our most recent call, we changed it. So 2 is pointing to 1, which then points to null. So we have the 3 here pointing to 2. We got that. And now the most recent function call made it so 2 points to 1 points to null. So I think that's about it. I hope that's clear, and we'll move on to the code. Here is the code for the recursive approach. So as I mentioned on the whiteboard, the first part is the base case. We're going to be checking if the head is equal to null or if the head.next pointer is pointing to null. In either case, we'll be returning head. Otherwise, we're going to be continuing on with the rest of the code. The first part of that is initializing a variable called reversed list head, which is going to be making recursive function calls to reverse list with head.next. So as you can imagine, this will be taking place until we get to the final element in the linked list or final node. At that point, this head.next equals null clause is going to be activated, and we'll be returning the head because the next pointer, what 5 is pointing to, is null. Then we'll be doing the reversal stage as I showed you on the whiteboard. We're assigning head.next.next to head and head.next equal to null. That's just swapping out and reversing. Finally, we'll be returning the reversed list head because at the very end, that's going to be the first element of the reversed linked list, which gives us the rest of the list. If I run this now, it'll pass the test cases, and now I can submit it. Great. The final thing I want to touch on is the time and space complexity of this approach. So the time complexity is O of n, where n is the size of the linked list. We make recursive calls for every element in the linked list. The space complexity is also O of n because of the recursive call stack space required. We're making a recursive call for every single element in the linked list, and that's equal to the size of the linked list.